Hey, welcome back. So this section is about a topic called recursion. And I think often recursion comes with a lot of baggage. A lot of the students that I've taught in person have heard of the term recursion and approach it with a bit of apprehension. It's somewhat intimidating. And I think that's because it's a little bit tricky to wrap your head around at first. But then once it clicks, it's one of those things that once the pieces fall into place, I think most people don't struggle as much to understand it, and they don't have to. It becomes sort of second nature once you understand how it works. But there is a bit of that first hurdle. And what I want to do, I'm not trying to scare anyone, but what I want to do is actually teach the exact way that I was taught recursion. In my first computer science class in high school, AP Java, there was this teacher. Oh my gosh, what was his name? Mr. Carlson. There we go. I remembered his name. And he read a story to us, a very short story, that helps explain this idea behind recursion. So all that I'll say to preface this is that recursion is it's a different way of thinking about writing solutions. So we can write a solution to a problem the non-recursive way, which is called iterative or iteratively. And then there's also the recursive way. And I know that's insanely vague. So first I'm going to hop into this story. It shouldn't take more than like 30 seconds or a minute. Once upon a time, there was Martin, a little boy named Martin. This was way back before there were computers, back when there was wizards in our world. There were wizards, at least, and alchemists. And there's this little boy named Martin who was training with them. And there was an angry dragon named the Dragon. And he happened to look like the new dragon emoji. So one day, Martin is talking to some wizard, and this wizard gives him a task. The wizard says, I need you to go talk to the dragon, and I'm going to give you a list of numbers, and I need you to come back and tell me if any of the numbers on that list are odd. And they didn't have computers, and they, for some reason, were unable to do this on their own. They needed the help of the dragon. So Martin goes up with his list of numbers. You can see it here. And he says, excuse me, Mr. Dragon, can you tell me if any of these numbers on the list are odd? And the dragon is not in a very good mood. He's a little hungry. It's been a while since he had something to eat. So he's angry. And he says, I'm sorry, boy. I'll only tell you if the first number in that list is odd. So he's not super angry. He doesn't immediately burn him alive and eat him. Instead, he just says, sort of grumpily, I'll only tell you if the first number in that list is odd. And Martin is very upset because he doesn't want to fail at his task. He says, I need to know if any of the numbers are odd, not just the first one. And the dragon is even angrier, and he says, sorry, I'll only tell you if the first number is odd. That's my final offer. That's all I'll do. So then the boy has a little bit of a think. What could he do? And Martin comes up with a solution. He goes to the dragon, and he says, okay, fine. What about the first number in this list? And he gives him the whole list. And the dragon says, that's not odd. It's even, as we can see. Then Martin comes back and he says, all right, what about the first number in this other different list? It's not odd. He does it again. What about this number, the first number in this list? Is that odd? And the dragon says, it's not odd. And the dragon's getting pretty bored. And then finally he says, what about this number in this list, the first number? There's only one number left. It's not odd. And then finally, Martin comes back one more time. What about the first number in this list? And it's an empty list. And the dragon is very upset. He says, that's an empty list, you moron. There isn't a number in there. How could anything be even or odd? There's nothing in there. And then Martin triumphantly says, aha! So all the numbers are even in that list. And then the dragon says, I never said that. I only told you if the first number of a list was odd. So then Martin gets out a pen or pencil, or I guess a quill, or maybe just a stick in the dirt. There we go. And he starts drawing, and he says, well, I gave you this first long list. You said the first number was not odd. Then I gave you this shorter list, and you said the first number was not odd. Then I gave you this other list. You said the first number was not odd. Then I gave you this list. You said the first number was not odd. Then I gave you this empty list, and you got really mad at me. But you said that there's nothing in there to be either even or odd. So I can conclude that there's no odds in this list. There's no odds in that list. No odds in that one and that one. And finally, there are no odds in the entire first list that I asked you about. So no odds. And the dragon says, oh, congratulations, boy. You have discovered recursion. He's very condescending. And then Martin is slightly puzzled, and he says, wait, you knew about this the whole time? And it turns out this whole thing was just a test. That's the way I spin it. It's a test, because otherwise it's a pretty big waste of time to send this kid to a dragon. It's a pretty dangerous operation, honestly. Dragons are very unpredictable, just to find out if the list of numbers is odd. But on that day, Martin discovered recursion. So that's the way that I was first introduced to recursion. I'm sure you could update that and make it a little more exciting. But the idea is basically taking one problem and doing it over and over on a smaller piece or on a changing piece until you hit some endpoint, which we call the base case. So we'll get to that. First, let's talk about our objectives for the section. So we're going to define more specifically what recursion is and how it's useful. We'll understand the two essential components of writing a recursive function. There's two things that have to be there. Then we're going to talk about something called the call stack, which if you haven't heard about, I'll explain what it is. And then we'll also talk about how it relates to recursion, how we can use the Chrome developer tools to debug the call stack and recursive function calls. We'll talk about helper method recursion and pure recursion and compare them. And we'll solve a bunch of challenges and have a ton of exercises. So this is going to be a little bit of a crazy ride for this section. We've got a lot to talk about. Remember what I said, recursion takes a little bit to click. Once you get it, you get it. But if you struggle with it, that's totally normal. I have seen many students take days that sounds scary, but take a lot of time to get it. But then once they get it, they understand it, and it's not a problem. So don't beat yourself up. If you have to review some of this or come back later, in an online course, I know it's hard because it looks like this is, 6 or 7 videos of content, and it only takes maybe 30 minutes or an hour to watch it all. But that's not the time that I intend for somebody to really take to absorb the content. So just keep that in mind. If you're feeling behind, that's normal with this. It's tricky. Okay, all right. So we talked about objectives. We did that little story with Martin and the dragon. Now let's actually get a formal definition of what recursion is. And secondly, let's talk about why you should care. I did a little bit of, I wasn't trying to scare anyone, but I did a little bit of talking at the beginning about how recursion can be tricky. So let's talk about why it's worth it, why you should care, and why you should push through it if you do have a hard time getting it right away. But first, a definition. What is recursion? It's just a process that calls itself. And in our case, in everything we do in JavaScript or in code, when we say recursion, we're referring to a function that calls itself. So we've seen many a function that calls other functions. That's very, very common. We could have a function called laugh, and inside of it, we would call console.log potentially. That's a function call inside of a function. What's different about recursive functions is they call themselves. So our laugh function inside would call laugh. And you can imagine, first of all, that might make your head hurt already. But then imagine that it's happening over and over and over again, and there has to be some endpoint. Or if we go back to this slide here we have, imagine that we have a function called check for odds. We would call it here, and then in check for odds, it would call itself again on a smaller list. And then that would call check for odds over and over and over again. There has to be an endpoint, of course, or else we just keep going like an infinite loop. But it's slightly different than an infinite loop. But we'll get there. So let's leave it at that. It's a function that calls itself. Now, why should you care? Why do you need to know this? There's a bunch of reasons. First of all, it's everywhere. It's used all the time. We're going to use it a lot in the course for a lot of the solutions we write later on. But even before that, if you've been writing JavaScript, you've probably been using recursive functions without knowing it. Things like json.parse or json.stringify. If you've ever made an AJAX call and gotten JSON back and turned that into JavaScript, then you may have called a recursive function. Now, json.parse, json.stringify are up to the JavaScript engines to implement. So Mozilla has their own, Rhino, I think, their own implementation where they write json.parse how they want to. And it doesn't have to be written recursively, but it often is. So the point that I want to make is not that it's guaranteed that you've called a recursive function, but that json.parse is often written recursively. And actually, I have the source code open for Rhino, and this is the engine that Mozilla uses, and it's written in Java, so don't worry about the syntax. But if we look, it's not as simple as json.parse calling json.parse immediately. Instead, there's a function called readValue, this method here. And read value calls things like read object. So let's just focus on those two. Read value, you call that, it calls read object. Well, if we look at read object, in the middle of read object, if we scroll down a bit, it calls read value again. So then read value is called, and that could call read object, and we end up with this cycle where even though it's spread across two different methods, they are calling each other. So read value is calling read object, which is calling read value, which calls read object, and it's this cycle that goes over and over and over. So that's an example of recursion. But let me show you a simpler implementation. Here's a simpler implementation written in JavaScript. So this is not actually what's used in any of the browsers because browsers aren't written, JavaScript isn't written in JavaScript, but here's an implementation to show what it would look like. So I'm going to take a look. There's this method called walk, which is, here's JSON.parse. So it's called walk. And inside of walk, it's calling walk. I don't know if you can see that. Oh no, I lost it. There we are. So walk is called inside of walk. It calls itself over and over. I'm getting tired of saying the word walk. It starts to sound very bizarre when I repeat it that much. But what it's doing, if you think of a JSON, a string, it's all nested. When it says walk, it's going to move down sort of to the next line or to the next thing to parse over and over and over until it hits the end. Okay, so a bit of a tangent, but maybe somewhat interesting. Those are two examples, JSON.parse and stringify. Document.getElement by ID and DOM traversal algorithms. So remember that the DOM is this tree structure where we have all these nested things. They could be 100 layers nested, full of a div inside of a div inside of a div. And if we're trying to search through all of them, one popular approach is to write code that does it recursively. Object traversal, which is just like traversing JSON. Now, aside from these functions like JSON.parse and getElement by ID, query selector, things that we've used before probably, we're also going to be writing a lot of our own recursive functions later on. So when we write our own data structures, when we create trees or graphs, for example, when we want to traverse them, when we want to search for something across them, often the solutions involve recursion. Now, remember, you don't have to do anything recursively, but sometimes it's easier. Let's put it that way. It's cleaner and simpler to understand rather than doing it without recursion. And I just got ahead of my bullet point here. It's sometimes a cleaner alternative to iteration. So we'll see some examples. We're going to write a couple functions both ways, with and without recursion. And I think we'll make it a little clearer that sometimes it's nicer. So why you should care? One, it's everywhere. You've been using it. That doesn't really matter, I guess, because it doesn't impact how you use things like JSON.parse, but it really is important once we get into these more advanced data structures and we're writing our own parse functions or our own getElement by ID, traversing a tree, for example. All right, so I'll leave this video off here. Okay, so we're almost to the point where we're going to write our own recursive functions, but first we have to talk about one important thing, which is what happens behind the scenes when functions are called in JavaScript. If a recursive function is calling itself over and over and over again, what happens behind the scenes? And this is important for us to understand in order to write effective recursive code that doesn't break. So in almost all programming languages, there's some data structure behind the scenes that's managing function calls. When they're invoked, often are waiting on other functions to return. There's a special order that happens, right? Functions don't just happen randomly. Like if you have a function called first, and then inside of that function, it calls a second function, you need them to go in the correct order. And so there's a data structure in charge of that in JavaScript called the call stack. So you can think of it as a stack of papers or something. It's actually a data structure called a stack that we'll learn about later. You might have heard of stacks and queues before, but all that we're going to say for now is that when a function is invoked, it's placed on the top of the call stack. So just like if we have a stack of papers on our desk, the newest one that we put on goes on top. And then when JavaScript sees the return keyword, or when a function ends, there's no more code to run, the compiler will remove the top item from the stack. So the idea of a stack, the reason I'm saying a stack of papers on a desk is that you put something on top. When you remove something, you also remove from the top. You don't remove from the bottom of a stack of papers. You take whatever's on top. So that's the idea of the call stack. What I'm going to show you now is what it looks like in the Chrome DevTools when we have a couple of function calls, what the stack actually looks like, how it reflects those functions. Okay, so I have a snippet here that I've made. It's very silly, but it has 4 different functions. There's a function called wake up, and wake up calls take shower, eat breakfast, and then it prints at the very end when everything's done, okay, ready to go to work. So wake up is invoked down here, and then wake up calls take shower, and take shower is simple, it just returns showering. Then we have eat breakfast, and eat breakfast is called, and it's a little more complicated because it sets a variable meal equal to cook food, which is another function. So cook food is going to then be called, and that returns, well, there's a list of items and it picks one at random. So it's going to pick one of these three things. That's what this code does, and just return it. So cook food might return eggs. Then eat breakfast was waiting on that. So meal is now eggs. It returns eating eggs. And then wake up was waiting on that. And it, because of eat breakfast, that was holding things up. Then we move on finally to console.log. Okay, ready to go to work. So I'm going to show you, I'm going to step through this one at a time, one function call at a time. And the way I'm going to do that, over here I have this call stack window open. And I'm going to add a breakpoint here. So as I hit this little button to run it, or command enter on a Mac, what's going to happen is that over here we'll see things added to the call stack. So I just hit command enter, and I'm going to step through it with this little thing here, this arrow. So first thing that happens is that we get to wake up, and you can see wake up is on the call stack now. It's the first piece of paper put down. But wake up isn't resolved. It hasn't returned something. It's not done. In fact, the very first thing it does is call take shower. So take shower is added onto the call stack. So now we have this stack with two function calls on it. So take shower is simple. It just returns showering, and you'll actually see that right here. So we're on take shower now. Return value is showering, and then it's removed from the call stack because it returned a value. Then we move on back to wake up. The next part of wake up, we already did this. Now it's on to eat breakfast. So eat breakfast is added to the top of the stack, and you can see eat breakfast isn't as simple. Eat breakfast is going to call cook food, and cook food is added to the top of the stack. So now we have wake up, which is still waiting for eat breakfast. Eat breakfast is waiting on cook food. So cook food is first, it makes this array of items. You can see that in the local scope, items is created now. Next line is going to pick a random item and return it, which is what happens. We returned protein shake. So now cook food is done because it returned, and we return back to, or I shouldn't say return, we go back to eat breakfast, which was waiting on cook food. So now you can see in eat breakfast, meal in the local scope is equal to protein shake. So we're going to return eating meal, and we return eating protein shake. So it returns, which means that eat breakfast next is removed from the stack. It's done. And finally, we go back to wake up, which has been waiting patiently this whole time, and we are able to console.log, okay, ready to go to work, which you'll see appear down here. Okay, ready to go to work. And now we're done with wake up, and we've finished now. We're at the end. There we go. So there's a lot going on there, but the idea behind it is that as functions are invoked, they're added to the top of the stack, and then they are popped off one at a time from the top as well. So the reason that we're going over this, first, hopefully that was clear, what's happening there. These dev tools are useful. If you've never seen the call stack tool over here, it's very nice to be able to step through and understand the order things are happening in and what's waiting on what. But the reason I'm showing it to you now when we're discussing recursion is that when we're writing recursive functions, we're going to be working with the call stack a lot. So you're probably used to functions being pushed on the call stack and popped off right when they're done. But with recursive functions, it's different. They keep pushing new functions over and over and over onto the call stack. In fact, the same function over and over and over, and it's waiting to be called. So if we take this idea of json.parse calling json.parse, and it keeps calling itself over and over and over, the call stack is going to look like json.parse, 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 but it has to end somewhere. And that's what we're going to talk about in the next video when we actually write our first bit of recursive code, is where it ends. We've established that a recursive function calls itself, but how do we know when it stops? Because otherwise, isn't the call stack just going to continue to go forever? And we'll talk about that as well. So hopefully this made it a little bit clearer what the call stack is. It's this thing behind the scenes in JavaScript that it's a stack data structure, which all that means is that things are added to the top and removed first from the top, and functions, when they're invoked, are added to this structure. So next up, we're finally going to write some recursive code. All right, welcome back. So in this video, we're finally going to write our first recursive function. So big moment. And the first thing we should do is just talk about the game plan for any recursive function. There's two things that must be present. So the idea is that we're invoking the same function over and over, having one function call itself recursively, but there has to be a stopping point. And that's the second piece, which is called the base case. So the base case is where the recursion stops. There has to be an end of the line. It doesn't just continue to call itself over and over and over and over forever. That would be a huge problem. Just like a while loop has to have some place to stop, otherwise it just goes forever and makes your computer angry. So if we go back to this example with Martin and the dragon, every time, let's say that this represents a single function call. Let's call it check for odd numbers. And it's called over and over on a smaller piece of data each time, but that doesn't just go forever. There's a clear stopping point. The code, if we were to write this, and we can do it in a bit, the code would basically have a conditional to check, is the list empty? Is there an empty array for numbers? If that's the case, then stop. So the two essential parts of any recursive function, the base case that has to be there, that's the end of the line, that's where the recursion stops. And then different input, I couldn't really think of a good name for this, but basically the recursive call, you're going to call the same function over and over, but each time you want to call it with a different piece of data. You wouldn't want to just use the same list of numbers and check for the first item in that list to see if it's odd over and over and over, because you would never get anywhere. What you would want to do, or in that with the Martin and the Dragon solution, we change the list. We basically chop off one number at the beginning and then pass the list through again and try to do the same thing until we hit an empty list. So there's the different input, and then there's the base case. So let's take a look at a real example now. Our first simple recursive function, it's called countdown. It doesn't do much, it just prints numbers. Starting from whatever number we pass in, let's say 5, it will print 5, 4, 3, 2, 1, and then all done. So I have it in a snippet, there we are. If I execute this, you'll see the output is 5, 4, 3, 2, 1, all done. So we could easily write this without recursion, do it iteratively. I went ahead and typed it up. We could do something like this. Let me comment that one out. Function countdown takes a number. We just loop. Start I at the number, like 5. While I is greater than 0, subtract 1 from I each time. And let's verify that it works. Now, let me clear this just so we can double check. There we go. So we go 5, 4, 3, 2, 1, all done. Okay, so I just wanted to show that you can easily do this without recursion, and that's not the point. This is something that we all are familiar with, just looping and printing numbers, but to do it recursively is a bit different. So let's walk through how it works. When I call countdown, let's do something simpler. Let's do 3. Countdown with 3. Well, let's just walk through line by line. Is number less than or equal to 0? No, it's 3. So none of this happens. So all we do is print 3, then we subtract 1 from num, and then we call countdown with num, which is now 2. So we print 3, so we can, if we step through, basically print 3, then the next line, num is now 2, so we call countdown with 2. So then let's start over. Is 2 less than or equal to 0? Nope, so we skip this. We console.log num, so that's going to be print 2 again. We subtract 1 from num, turning it into 1, and we call countdown with 1. Then starts over, countdown of 1. If num is less than or equal to 0, that's still false. Console.log num, so then we print 1. I cannot spell print. Print 1, and then countdown of 1, or excuse me, countdown of 0, because we subtract 1 from num, giving us 0. Start over, countdown of 0. Now, this is our base case. This is the end point. Otherwise, if we didn't have this, we'd keep going into negative numbers and just forever. So what is our base case? Is num less than or equal to 0? Yes, now it is. Num is 0. So num is less than or equal to 0. So we console.log all done. And then this is important. We return. And we're not returning anything, but we have to have this here, because if we didn't, if we just printed all done, then we'd keep going, right? Console.log 0. Num minus minus would be num is -1, and we call countdown with -1. So we have to have this return in order to stop it. Or I guess if we wanted to, we could wrap this all in an else. So hopefully that's clear what happens. Let me just add our final print, all done here. So you can see when we call it with 3, it calls itself countdown with 2, calls itself countdown of 1 with 0, and then we hit the base case and we stop. Okay, so hopefully you survived that first recursive function example. Now we're moving on to our second example. So this is what it looks like. It's called SumRange. And first, try and identify 2 pieces. Can you identify the base case? So a key hint for that is there's only 2 lines here, but a base case almost always involves a conditional to check for something, and then it returns something. That's the end. That's the bottom of the well. You hit the water. You hit the rock. I don't know. That's a terrible way of putting it. There's an endpoint. Then there's the different input, which I'm still not happy with that term, but there's the recursive call, which we're calling with a smaller piece each time. So in the last video, we were subtracting 1 from num and calling countdown again. Num keeps shrinking towards eventually the base case. Here, we're doing the same thing. So the base case to start is this line. If num is equal to 1, return 1. And that makes sense. I mean, first of all, if we tried to just do some range of 1, if we're going to add all the numbers between 1 and 1, we should just return 1. So that's the base case. And then here is our recursive call. Return num plus some range num minus 1. So this gets a little bit crazy, I know, because we have more than one return in here. We're going to step through this one little piece at a time. But think of it this way. If I plug in 3, we're going to start, this is not true, so we skip that. And this is going to return 3 plus some range of 2. And some range of 2 will return 2 plus some range of 1. And some range of 1 returns 1. And then all those things are added back up, waiting on the call stack, and we end up with, 6? So I have it over here. Let's just test it out quickly. If I do some range of, let's do 4. That's going to give us 10, as you can see there. Okay, and 3 should give us 6, and it does. So let's actually walk through what happens. If you feel good about this, just move on and skip this, because I am going to do a detailed walkthrough, just because, it really helps. I think, in my experience, it helps if anyone's struggling to understand what's happening. This is a bit different, because we're not just printing. We're returning and returning and returning and returning over and over and over. So let's walk through this. I call some range of 3. So that's the first thing I do. This is not true, so that doesn't matter right now. Num is 3. But then that's going to return, so if we just write I don't know why I'm doing caps. There we go. Return num, which is 3, plus some range of 2, right? Okay, so some range of 3 is this right here, and it's waiting for some range of 2. Some range of 2, if I tab over here, is going to be called, is num 1? No, it's not, so we skip. So that returns num, which is 2. So I'll try and do this in the middle here. Return 2 plus some range of num minus 1, which is 1. Like that. Okay? So we have some range of 3, the first thing we called. It's waiting. It's basically trying to add 3 to some value, but it doesn't know what yet. Some range of 2 has to be computed, but that's waiting because some range of 2 is going to return 2 plus whatever some range of 1 is. And then finally, some range of 1. When num is equal to 1, this is true. So we return 1. That's our base case. This stops us from free falling forever to a rapid descent. We're returning 1. That's the end. There is no further recursive call. So when we return 1, what happens? Well, this was waiting to see what some range of 1 was. So that gets simplified. That turns into 1, right? So this returns 1. So then this turns into 1. So then some range of 2 is going to return 2 plus 1. This now has a value, which is 3. So then some range of 2 returns 3. Let me just delete it and put it back up here, which some range of 3 was waiting. Some range of 3 basically knew it was going to be 3 plus whatever came back from some range of 2. Well, finally, there's a value that came back. It's 3. So it returns 3 plus 3. which finally returns 6. And that's our answer. So it's kind of complicated to draw out. I picked a small number like 3, but as we go higher and higher, there's many more function calls on the stack that we have to worry about. So we can view this. Let's do the same thing. Let's do 4 this time. And I'll put my breakpoint here. If you grasp this already, skip it. But let's do it now. So we step through. First thing that happens, well, I have to execute it. Command enter. Okay. So first off, sum range of 4 is called. That's added to the call stack. This is waiting. Num is 4. Well, it's not waiting yet. It's being executed right now. This is not true. Move to the next line, and it's going to return 4 plus sum range of 3. So it's going to wait because it has to have an answer from sum range of 3. So you can see in this sum range right here, num is 3. Down here, num is 4. So it's going to do 4 plus whatever this answers or returns. This can't return anything just yet because its return value is 3 plus sum range of 2. Num minus 1 is 2. So if you watch over here, as I go to the next step, we get another sum range added to the call stack. In this one, the local variable num is 2. So this first part's not true. Move on. It's going to return 2 plus sum range of 1. So finally, our call gets added up here. So now we have another function call added for sum range. This time though, num is 1 in this context. So num is 1 which means this is true. So we finally return 1. So remember, this is waiting here. This is waiting on the return value of this. This is waiting on the return value of that. This one is waiting on the return value of this one. This is going to return 1. So when that happens, right here, there we go. Return value 1. And then watch as it gets popped off. There we go. This function now, which was waiting, it was adding 2 plus the return value of sum range 1. Well, that now has a value. It's 2 plus 1. So it returns 3. Then this one, when it returns 3, fills in the blank for this second call, which was waiting to see what sum range of 3 was. So then we get that answer, returns 6. And then finally, this sum range, which was waiting the whole time patiently to add 4 plus the sum range of 3, which came back as 6. So we get 4 plus 6, which is 10, and it returns 10, and we're done. So I know that there's a lot there, but I hope that explanation helped out a little bit. It's always nice to walk through the call stack, but this one is different than the last video where we just were printing things out. In this case, whatever is returned from the base case matters. It's added on to what the previous function call was waiting for, and then that's added on, and it has this reverse cascade going back up. Okay, hopefully that makes a little sense. We have a couple more examples. All right, welcome back. So we have one more basic recursion example here, and it's probably the most classic example of the most classic intro to recursion function that's used, which is factorial. So if you're not familiar with factorial, it looks something like this as a mathematical expression, exclamation point. You don't read that as 4. That's just 4 factorial, which is equal to 4 times 3 times 2 times 1. And, 10 factorial is 10. I'm not going to type the whole thing out, but 10 times 9 times 8, all the way down until 1. So you could easily do this without recursion, just like all the other things I've shown you so far. How would you do that? Well, hopefully you can visualize it now, but use a for loop. And like here, let's define our function. We'll just call it function factorial. It takes in a number. And then let's make a total variable. Let total equal 1. And then we'll do a for loop. So let's do I equals num. Keep going while I is greater than 0. And then do I minus minus. And then we'll just multiply total. So total times equals I. And then at the end, return total. Should work. So total starts at 1. If num is 3, we're going to loop for I equals 3. So the first time through, we multiply total by 3. So we get 3. Then we subtract 1 from I. It's 2. So we multiply by 2 next time. We get 6. Then I is 1. So we multiply by 1, which technically we don't. Well, let's just make sure it works. I'm going to run this. So let's just do factorial of 3. Okay, we get 6. Factorial of 4, we get 24. Okay, so it's working. There's one small change we can make just to eliminate some redundancy. If total is already 1, there's no reason to multiply by 1 at the end because we're multiplying by 3 times 2 times 1. So we can just do this. I is greater than 1. We multiply by 1. And it still works. Okay, so that's the non-recursive solution, the iterative solution. Next, let's do the same thing, but recursively. Welcome back. Let's do the same thing, write factorial, but do it the recursive way. Okay, so what we need to do, the first thing, aside from just defining our function, the first thing is going to be to understand both the base case and the smaller chunk, the recursive call, the different, whatever we want to call it, basically the two different components. So let me just define it here. It takes in a number like this. And what we're going to do, factorial of 3 is equal to 3 times the factorial of 2. Factorial of 2 is equal to 2 times the factorial of 1. So what we're going to, at the end of the day, we're going to return here num times factorial of num minus 1. So hopefully this part makes sense. But if we just had this, this would be problematic because there's no stopping point. If num starts at 10, then we're going to return 10 times factorial of 9. But then factorial of 9 returns 9 times factorial of 8. But it keeps going. It goes past 0, goes to negatives, and it will go forever. So that's not good. So we need to have the endpoint. Well, what is our endpoint? Well, we kind of can take what we did in the iterative version. We multiply by 1. That's the end of the road. We don't want to keep going to 0 because if we multiply by 0, it eliminates all of our hard work because it wipes everything out, the magical power of 0. So we'll just do something like if num is equal to 1, return 1. Factorial of 1 should be 1, right? If we plug 1 in here, we should get 1 right away. 1 times 1. There's nothing below it to multiply by. And this is it. This is the solution. So it's short. And if we step through it, let's do it with 3 again. It's the same idea behind the last one we did with sum range, right? It looks identical, except we're multiplying instead of adding. So factorial of 3 is going to return 3 times factorial of 2. Factorial of 2 is going to return 2 times factorial of 1. Factorial of 1 returns 1. So then we work back up. So if we just really quickly do this, factorial of 3. Actually, let me do factorial of, let's do 5, a little bit larger, just to show you. And I'm not going to go through it step by step. We're just going to very quickly look at what happens to our stack over there as it continues to grow. Okay, so now num is 1. So we have 1, 2, 3, 4, 5 calls here. Num is 1, which is returned. So then we work backwards. You can see the return value growing. From 1, it then is multiplied by 2, then by 3. Now we're going to multiply it by 4. We get 24. Then we multiply it by 5, and we get 120, and then that's the return value, 120. And you can see the console shows us, it displays the return value of 120. All right, so that is recursive factorial, a very, very common intro to recursion exercise. And it's a pattern, as I already explained, it's basically the same thing here, except we're multiplying now instead of adding. Welcome back. So what I want to do now in this video is talk about some of the pitfalls, the common problems that arise when you're writing recursive solutions. So one thing that happens more often than you might think is that you don't have a base case or your base case is wrong. So what I mean by that is that if we go back to factorial here, without this base case right here, this code just keeps going and adding function calls to the stack over and over. So if we just plugged in 2, factorial of 2, it's going to return 2 times factorial of 1. Factorial of 1 is going to return 1 times factorial of 0. Factorial of 0 returns 0 times factorial of negative 1, and it just keeps going forever. There's no end in sight. And if I do run this right now, you'll see what we get. Maximum call stack size exceeded. So this means that, actually, I don't exactly know what will happen if we do try and step through this. But if I try it out, you'll see that our stack just continues to grow over and over and over. So I could keep clicking forever and stepping through this. We're at 100 something calls on the stack right now. But there is a maximum size. It does differ depending if you're on Node, what engine you're using. I think that it's somewhere around 10,000 calls. I'm not positive though, but there's a maximum and we're going to exceed it. So if I just resume the script execution, you'll see we get that error. Maximum call stack size exceeded. Okay, so that's a big problem. Another thing that we could run into is returning the wrong thing or forgetting to return in the first place. So what I mean by that is if instead of returning, so let's say we have our base case, the correct base case, so it should stop. But what if we were just returning num times factorial of num? And this is a simple example. It's easy to identify the problem, but sometimes your code is a lot longer, and sometimes it's harder to walk through each individual step if you don't take the time to pay attention to what you're actually returning. Because even though we have our base case, it doesn't help. We're never going to hit it because we're returning, in the case of factorial 2, we're returning 2 times factorial of 2, which is going to return 2 times factorial of 2 and spin forever. Well, not quite forever, as you'll see. We hit a problem. There we go. Maximum call stack size exceeded. One more potential pitfall is if instead of a return here, if we had a console.log 1, for example. So we still have the base case. Oh, let's change this back to num minus 1. So everything looks good except that we're console.logging 1 when num is equal to 1. And what do we get? Same thing. Maximum call stack size exceeded. Because we printed out 1. Here, if we, let's refresh and do the same thing. Step through this. If we look at the call stack, okay, so factorial of 2 is called, so we return 2 times factorial of 1. Well, factorial of 1 isn't returning anything, so it doesn't stop execution here. Remember, that's the way that we pop this thing off the stack is by returning, but we're not returning 1. So instead, this is just a nice little extra thing. Oh, by the way, if num is equal to 1, print out 1. But then keep going. Return 1 times factorial of 0. So you'll see that's what happens. Num is now 1. We return 1 times factorial of 0. Now num is 0, and we keep going. And if I keep clicking, you'll see num keeps going down, -7 now we're at. And we'll keep going until we hit the maximum call stack size, or we exceed it. So I'm going to fix that and put it back as return 1. So the importance of returning is, that's what recursion is built on. The idea of this call stack where all these things are dependent on one another, waiting, they're kind of primed in a chain, but we still have to return some value at the end to then send back and then to add or multiply or do something with to send back to the previous one to keep going until we get to the original function call of factorial 2. All right, so let's just make sure it still works. Let's do factorial of 5. What do we get? 120. Okay, it's working. Now, one note, in Chrome, the message it's giving me is, maximum call stack size exceeded. This is generally what's known as a stack overflow. Think of the stack, it's overflowing, right? Too many frames on that stack, too many functions trying to be called. So you've probably come across that term before in the name of a popular website, Stack Overflow. That's where it comes from. When you have, usually it's a recursive call. If you see that message, just keep that in mind. This means that your recursion is not stopping. There's never rock bottom. Okay, so that wraps up what I want to say about common problems. You don't have a base case, or you're forgetting to return a value, or returning the wrong thing. All of those can result in a stack overflow, which is not good. Welcome back. Next, I'd like to introduce a design pattern that's commonly used with recursion, called helper method recursion. So far, all the recursive functions we've written are single standalone functions like factorial. It is recursive itself. We call factorial from outside the function, and factorial itself calls factorial inside its own code. That's been the case with all the functions we've written so far. With helper method recursion, it's a little bit different. So this code doesn't actually do anything. This is sort of just a pattern that I'm laying out. But with helper method recursion, we have two functions. We have the outer function here, and then inside we have our recursive function. So this recursive function calls itself, as you can see here. Again, this is just the pattern. I'm going to show you a concrete example that does something in just a moment. But that's why it's called helper function or helper method recursion. we have our main outer function that we would call, like as a developer from outside here, we would call outer and pass something in. And then inside the code of outer, there's another function defined, and it calls itself recursively. So this is commonly done when we need to compile something like an array or a list of data. We're not simply tabulating, we're not multiplying one value over and over and over like we were with factorial or summing different, summing range. That was another one we did. If we're doing something like this, collecting all the odd values in an array, it's very easy to do helper method recursion. We create an empty array where we will then store our data in, and then we call our helper function. So the reason we do this, if I just tried to define a function called collect odds, which accepts a list of nums, if I tried to make a variable called result, and I set it to be an empty array, this is where we're going to put the odd numbers. Well, if we're doing a recursive function, no matter what I put after this, every time it's called, result will be reset to be an empty array. So how are we going to collect our data? How are we going to have, this piece that persists throughout? And one easy solution is to define result outside of collect odds, like this, and then add to result in here. And rather than having result float around in the middle of nowhere like this, we use helper method recursion, which really just means defining a function around it. So here's my solution, or a solution to this problem. Oops, looks like I'm missing a bracket. Update that slide. Oh, there it is. Okay, zoomed in too much. So what we have here is collect odd values, which is what we would actually call down here. We'll pass in, let's do a simple one. Something like this. And it takes that array in. It makes our result array that's empty. Then here's our recursive logic. And ignoring that for just a moment, we call the helper function, which we defined here, with the array. And then we return result that was defined up here. So this is going to manipulate result. It will be adding to result. And again, the reason we do this is that if we tried to define result inside of here, it would be reset to an empty array every time through. So with helper method recursion, we can get around that. And this is a common pattern when we are trying to compile some sort of result, usually an array or some other sort of data structure along those lines. So the actual logic here, if we do want to walk through this, if we look at helper, it's executed at the bottom with array. So this is array, this is passed in, and we have a base case where if the helper input is empty, if the length is 0, we just return. Otherwise, we check if the first input or the first element, mod 2, is not equal to 0. That means that it's odd. So if it's not divisible by 2 cleanly, it's odd. So we push helper input 0 into result. Then the next thing that we do is call helper, but this time we call it on everything else in the array, excluding that first element. So we make a subarray like this, a smaller array, and we pass that in to helper, and we run it again. And it's not empty, so we don't return. And then we take the first element, which is this, and we check if it's even or odd. Well, it's even this time, so this doesn't run. So then we call helper again, helper input.slice1. So this time, instead of this subarray, we look at this one. So we're always looking at the first element, and we're shrinking that array, and shrinking it until it's empty, and we return. Okay? So that's the logic behind it. But this pattern, whether it's odd values or we're doing something else, so later in the course, this is a flash forward. Do not worry about understanding any of this, but this is from the graph section of the course. We define a method called depth first recursive, which has a result variable. And this actually is, it's an example of helper method recursion. Here is the helper method defined inside of our other function. And we call it down here, and it's updating the result variable. Anyway, we'll come back to this, not the focus. I just wanted to show you that this is a real thing. I'm not just making it up or showing it to you for no reason. This is an actual traversal of a graph data structure, something a little more complex. Okay, so this is one way of doing the solution, but this is not the only way of writing collect odd values recursively. You can do it without a helper function. You can do it without having to define result outside in a different scope and then updating result. It's just that this is simplistic. It's easier to understand. In the next video, I'm going to show you how to do this the pure recursion way, which is not necessarily better. It's a little more confusing, but it is all recursion. There is no helper method. It's a little shorter, but we'll get there. That's coming up next. So helper method recursion is just a pattern where we have an outer function that's not recursive, which calls an inner function, which is recursive. Okay, I'll be quiet. Hey, welcome back. So the first thing I should say is that this video is paired, or it goes along with the previous video. We're going to solve the same problem in two different ways. So in the last video, if you didn't watch it, I recommend you at least skim it. We talked about helper method recursion, one strategy, one approach to solving this problem: collect odd values. So recursively, doing this iteratively is easy. We can use a loop and it's not difficult, but to do it recursively is a little bit more difficult. So collect odd values takes an array of numbers, even and odd, and it should return only the odd numbers extracted from that array without actually changing the original array. So helper method recursion was one strategy, but that's not the only way. We can do it with what's called pure recursion, meaning the function itself is totally self-contained and it's recursive. We don't have some external data structure like we had here, this external result array. We're not doing a nested function, helper method recursion. We're not doing any of that. We can do it with pure recursion. It's just a little more challenging. So here's the code. It is shorter, but it's a little harder to wrap your head around at first. So I'm going to copy this over and show you that it works. Here we go. If I execute the code, collect odd values on 1, 2, 3, 4, 5, it works. We get 1, 3, and 5. Now, if we walk through how it works, it's a little bit different. So we are defining this variable new array each time through. And if you remember in the last video, what I said was if you define this new array each time through, it's going to be reset to be empty. And that's true. This is going to be an empty array every time the function is called recursively down here. What's different is that we don't care. We want it to work that way. And what we actually do is concatenate all the arrays at the very, very end into one array and return that. So let me just walk you through what happens. It accepts an array, 1, 2, 3, 4, 5. That's what we'll start with. Then we define new array to be empty. We check if the array, the input, is empty. It's not. In our case, it's 1, 2, 3, 4, 5. Then we check if the first number in our array is odd. And in our case, it is. So we push that number, 1, onto new array. So at this point, our new array looks like this, just 1. Then we assign new array to equal new array, the current value, dot concat the result of collect odd values on the rest of the array. So array.slice1, if we take this array, for example, 2, 3, 4, 5, dot slice 1, it gives me everything from the first element onward. So ignoring the 0 element, or the index of 0 element, we get 3, 4, 5. So array.slice1 is going to take this array like that, collect odd values of 2, 3, 4, 5. So of course we're waiting, here's the recursive part, we're waiting for this to come back and return a value. And that's going to take a moment. So when we call that, we diagram this out, collect odd values 2, 3, 4, 5. We make a new empty array, new array. Array.length is not 0. It still has values in it, 4 of them. So we skip this. The first number is not odd. It's 2. So we skip it. We don't add it in. Then we get to this line. New array equals new array.concat, collect odd values, array.slice1. So new array this time is actually empty. This is what new array is. New array.concat, the same thing, collect odd values of the array 3, 4, 5. Sorry if you can hear that car honking outside. It's a bit ridiculous. 3, 4, 5, this array, slice 1. So speeding through the rest of this, when we call it next time, we're waiting on this collect odd values 3, 4, 5. Well, what does that return? Well, it's going to concatenate on a non-empty array this time. New array contains 3 because it's the first value is odd. And so then we call .concat on collect odd values on 4, 5. And then this repeats. I'm just going to copy this down. So this time it's an empty array because the first value is even. And then next time through, we're almost there. It contains 5. And we try on an empty array. And then finally, when we call collect odd values with an empty array, if it's empty, we return new array. Well, new array is just empty. So this finally returns this value. So we get an empty array. So then what happens? Well, this was waiting to concatenate this with whatever this returned. And this happened to return an empty array. Okay, so when we concatenate 5 with an empty array, it's just 5. Then we return new array at the end. So we return this. So we can replace this right here with that. So now we can, once again, we concatenate an empty array with this array. And that's going to give us this array. And we return it. So then here, collect odd values returned this. And we concatenate it with this, the array containing 3. So we end up with this array. So then we take this, and that's returned. And we fill it in there, and we concatenate it with an empty array, which just leaves us the same thing. We return that here, which is concatenated with this, which gives us our final return value, 1, 3, 5. So along the way, we use concat to help build up the result. If we just tried to push into new array over and over, it would be reassigned. Instead, new array is just going to allow us to either concatenate nothing, as you saw if I rebuild this. Oh, it won't let me go back. Well, a lot of the time with even numbers, we were returning an empty array or concatenating an empty array with another return value that wasn't empty, that contained an odd value. So we use concat to help us out here. And this is the pure recursion way of accomplishing the same problem. I think personally that helper method recursion is more straightforward. Yes, it does involve a little more code to make that second method, but I don't think that it's a big deal. And when you get to more complex logic and you're working with more difficult logic and data structures rather than just pulling out the odd numbers, you can always do it using pure recursion. You can make that work, but often I prefer to go with helper recursion. But in this case, I kind of like this solution. It's kind of cute doing all this concat over and over and over. Just to show you a couple of tips, when you're using arrays and you're trying to do a pure recursive solution without a helper method, you can use methods like slice, the spread operator, and concat that will make copies of arrays so you don't mutate them. And this will allow you also to accumulate some sort of result. Strings are immutable, so you'll need to use methods like slice or substring to make copies. And with objects, it's helpful to use object.assign or the spread operator. So we will come back to this later in the course. We will be writing quite a few recursive solutions.